This video is called Calculus Made Simple, and it's for science students, particularly if you've never taken calculus. And I'm going to apologize. All of my college math teachers have passed on, and for them I pray and I apologize because this is not rigorous in any way, but I'm hoping that it helps you to see the value of calculus and perhaps encourage you to study it more rigorously. Now, in science, we frequently come up with data. This is a graph that we got using some vernier instruments of the pH of a titration versus the volume of sodium hydroxide. As you can see, it starts off at a low pH because it's an acid, hydrochloric acid probably, and it rises gently and then it goes a swoop up, and then when all of the acid is gone, the sodium hydroxide increases the pH. And the point we're looking for is about here, where, for instance, an indicator would change colors. But in this pH titration, we'd like to know exactly what the volume is at which the acid and the base moles are equivalent. The first derivative of any function is the slope at any given point, the rise over the run. And so you can see we've put a little mark here. The computer has done this. And the slope is here a very tiny rise over a very tiny run, and it is symbolized by this tangent line here. Graphical programs can show the slope at each point as a tangent, and it can read off that number for you. Now, if you then graph the first derivative of the pH, which, remember, this is the slope at each line versus the volume, you will see in this case that where you had that big swoop up of pH, that you get a maximum. Probably the maximum is up here. And that's the curve's inflection point, where the curvature turns from positive to negative. And that's fairly easy to see here. It's not really very mathematically appropriate. The volume is obviously in the vicinity of 140. Can we get a little closer in accuracy? Yes. We then take the first derivative, which will be the second derivative, the derivative of this line at each point, and now we can get what we call the second derivative of the pH versus the volume. And what I've done is I've traced a straight line here using these points on either side of this swoop up and drop down. I've traced this line here to give you a better idea of the inflection point where the acid and base moles are equivalent. We can use this anytime we need the slope of a curve. Now the integral is the opposite. You have a curve, but you don't want the slope. You want the area in between a certain x and a certain other x. We want the area of the curve under the function line. So pick this up from the internet. The required area, we want to know what the area is between A and B. So we use the computer program, or obviously there are manual ways to do this, because what you're actually doing is you're adding each teeny weeny area here under the curve. And that will give you a number that is the area. And the smaller is the increment that you use for the dx, the more accurate you are with your area calculation.